End of the chapter. So we're introducing some concepts, but we won't really know what they mean because we need some more stuff before we know what they actually mean. So we're going to talk about vector fields, the curl, and divergence.
What chapter? 15.1?
What's that?
15.
Yeah, 15.1. All right, so in chapter 12, we talked about vector-valued functions. So a vector-valued function assigns a vector to a real number. And usually, if we were thinking about a physical problem, we usually thought of that real number as time. So we'd assign a position vector to a particular time. In a vector field, or for vector fields, assigns a vector to a point in space. So every point in space has a vector assigned to it. If we're talking about a two-dimensional vector field, it would be in the plane. So for example, our notation, we could say f of x, y, usually we write m I hat plus n j hat, and m and n are functions of x and y. And if we're in space, I'm just going to put plus p k hat, and p would also be a function of x and y. So we have these functions of x and y that give us our components of our vector. So that's a vector field. A vector field assigns a vector to a point in space.
Would that be functions of
X, y, and z. In the plane, it would just be the two m I hat and j hat. We just have functions of x and y. Example would be often you'll see vector fields in velocity fields in a liquid. So you have a liquid that's moving around. You assign a velocity to every point in the liquid. You could also, another common example, a gravitational field. We have we can assign a vector for the direction that gravity is acting at a particular point in space. And every different point in space has a different vector that represents the force due to gravity there. We could talk about electric fields or magnetic fields also. Can anyone think of a concept that we've talked about in the past that is a vector field? A familiar concept. The gradient is a vector field. Because del of a scalar function, del of f of x, y, z, is f sub x I hat plus f sub y j hat plus f sub z k hat. And these partial derivatives are functions of x, y, and z. The gradient is going to turn out to be an important type of vector field. Now we can sketch or we can visualize. One way to sketch or visualize vector fields, often they're very difficult to visualize. But one way that we can visualize them is by We can visualize them by looking at where the magnitude is constant.
Why can't we just draw them like a smooth field?
You can, but they can get kind of complicated. So I just want to look at a few examples. I'm going to bring up some pictures, and we want to match the graph of the vector field to the vector field itself.
Wow. Very
What did I do here?
You stopped. You did the last. Just trying to calm down. Why?
There we go.
That is.
All right. So and these are all equals. These are equals here. It's hard to see. Those are all equals. All right, so number one, we have our vector field f of xy is y I hat. So we could look at where the magnitude is constant. This one's a little easier. What's the only direction this vector points in? Yeah, it points in the x direction, and its magnitude is proportional to y. So which one is that going to be?
It only goes in the x direction. There's
Yeah.
only one that only goes in the
Right, there's only one that only goes in the x direction.
D.
It has to be d, and as y increases, the magnitude of that vector, the magnitude of the vector increases. So when y is bigger, the magnitude is bigger. So 1 has to match d. How about 2? See, so 2 only points in the y direction, and the magnitude is proportional to the x coordinate. So that's going to be c. So those two are pretty easy ones. Number 3.
No, 4 is definitely A because that was pretty slow. God, come on, Sam.
So let's look at we have some idea. Well, we can look at where where magnitude is constant. Constant magnitude, square root of x squared, or sorry, y squared plus x squared equals a constant. Well, this is x squared plus y squared equals some other constant. So this is going to have constant magnitude on a circle. So which ones of these have constant magnitude on a circle? That looks like an ellipse. So here we have a circle. So vectors around that circle have constant magnitude. Vectors around that circle have constant magnitude. The vectors around that circle have constant magnitude. Yeah.
Like where you got that?
The magnitude of this vector
I really like how you could guess very
is square root of y squared plus x squared. So we just found the magnitude and set it equal to a constant. So this is going to match A. And for number 4, we know that number 4 has to match B, but if we were going to analyze that, we would say the square root, the way we did this one, x squared plus 9y squared equals a constant. So x squared plus 9y squared equals some other constant, and that's an ellipse.
That's elliptical.
So that's going to match B. So this vector field has a constant magnitude on ellipses. All right, so we won't spend a lot of time visualizing vector fields, but it's good to have when you can look at these and have maybe an intuitive idea of how they're going to look. They do get kind of complicated, though.
You can try to visualize it like a slope field.
You can try to visualize them like a slope field. All right.
Can we see some complicated ones?
We will see some complicated
Who
ones.
wants to see some complicated ones?
The next thing we need to talk about is conservative vector fields. Conservative vector fields are very important types of vector fields because they have very nice properties, and we'll use those properties to help us with problems in the future. So a conservative vector field, if our vector field is the gradient of some scalar function, then f is called conservative. And the small function f is called the potential function. So if you've taken physics, a lot of this terminology should be familiar. This stuff that we're talking about in chapter 15 was developed to talk about electricity and magnetism. The theory was developed at the same time. So you talk about electric field and you talk about the electric potential. It's just the same idea. And remember that del f of xy is normal to level curves of f and normal to the surface f of x, y, z equals a constant. And this should be del f of x, y, z. So the property of the gradient as a normal vector is going to be important as well. So if you had a problem, and you will have some of these on your homework, if it said f of x, y equals sine 3x cosine 4y. And it says find the conservative vector field for the potential function. What is this asking us to do? Yeah, we want to find del f. So it's just asking us to find the gradient. The gradient of a function gives us a conservative vector field with this particular function as the potential function. This vector field would be a kind of a complicated vector field.
So hang on, this is just a clever way to ask us to find the gradient.
Right.
Just saying find the gradient.
Right. Because the gradient of a function does give us a conservative vector field.
Because people were catching
No. It's reinforcing the connection between the gradient and conservative vector fields. All right. So when we have a vector field, stop talking, folks. When we have a vector field, we want to be able to test to see if it's conservative. And we, in a little while, it'll take a few sections to come up with all of our tools, but we will talk about what conservative vector fields conserve. They should conserve something. All right, if f, our vector field, f of xy, is m I hat plus n j hat. And we're going to say m and n are nice functions. They have continuous first partials. Da, 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 da. This function is conservative if and only if the partial of m with respect to y equals a partial of n with respect to x. Why would that be? These are the mixed partials, right? This is the partial of our potential function with respect to x. And then this is the partial of that thing with respect to y. This is the partial or potential function with respect to y. And then that's the partial of that thing with respect to x. These are the mixed partials. So the mixed partials are equal. So if this function is, if this vector field is the gradient of a potential function, then these are the mixed partials. If it's not the gradient of a potential function, then these are not necessarily the mixed partials. All right, so this brings us to, we did in chapter 13, there was a bonus question that asks us to find a function such that these derivatives, the partial derivatives gave us these things. This leads us to kind of where that idea came from. So if you were given a question, is this vector field conservative? And if so, find the potential function. And I'm going to say f of xy in the plane, 3x squared y I hat, plus 2x cubed y j hat. This would be a relatively complicated vector field to visualize. So I'm going to say m is 3x squared y, and n is 2x to the third. This should be, I want this to be a, this should be a y squared. Well, it could turn out that it's not conservative. And then we're going to take the partial. Partial of m with respect to y is 6x squared y. Right? Partial of n with respect to x, 6x squared y. Those are equal, so it's conservative. Now we want to find the potential function. So what we're going to do is integrate the components So we're going to integrate the components. So we're going to say that f has to equal the integral of df dx, where f is our potential function. And in this case, that's going to equal 3x squared y squared dx. And f has to equal the integral of the partial of f with respect to y dy. So we're going to integrate the components with respect to their respective variables. And that's got to equal the integral of 2x cubed y dy. And the reason we set up two integrals, I'll show you in just a second, but we have to be careful. When we integrate this, what do we get? X cubed y squared plus a constant with respect to x. The constant can be a function of y. Because we're in it, this is a two-variable function. A function of y is constant with respect to x. And this is going to be, when I integrate this with respect to y, what do I get? X cubed y squared plus g of, I'll say h of x. This is a constant with respect to y. Well, the way that we can tell if we have to add some random function of x or some random function of y is if we integrated this and this had some extra function, some extra bit, or we integrated this and it had some extra function of x, or we integrated this and it had an extra function of y, then we'd have to add that to our potential function. But since these two are exactly the same, we can say f equals x cubed y squared plus a scalar constant. Now an example of where this would not work, where we'd have this extra function, let me look at it really quickly, is if the partial of f with respect to x was 1 plus e to the x, and the partial of f with respect to y was 2y. When I integrate this, what do I get? I get x plus e to the x plus f of y. And when I integrate this, I get, with respect to y, y squared plus some g of x. So here's my g of x here. Here's my f of y there. So I have to put those two together. So f would be x e to the x plus y squared plus some scalar constant.
So we still need this. So do we
Yes.
just add the two? And then if there's something that
Right.
matches, we only need one copy.
Right.
Why can't it be C?
It can be c.
Isn't it x plus e to the x?
Oh yes, this should be a plus.
Is that kind of like a bonus from
This was like, this example is like the bonus from chapter 13. Because you had some extra pieces that you had to add in there to get the whole function.
So if there's a piece that matches, you only put one copy, and then you just add on everything else from the integral.
Right.
So it's the two integrals sum unless they're matching.
Yes. All right. Well, we also want to talk about three-dimensional vector fields. Because we live in three dimensions. So with a three-dimensional vector field, we have this operation. New use of a symbol. So we have mi hat plus n j hat plus p k hat. Then the curl of f, and we write curl of f equals del cross f. So now we're using del as a vector operator, but now we're doing a vector operation on another vector. For the gradient, we made a vector out of a scalar function with the gradient. Here we're operating on another vector. So we're thinking of del is defined as this operator, the partial with respect to x, I hat, plus the partial with respect to y, j hat, plus the partial with respect to z, k hat. So the curl, del cross, the cross product. So del cross f is going to be this determinant, I hat, j hat, k hat, partial with respect to x, partial with respect to y, partial with respect to z, m, n, p. This is how we're going to calculate the curl. And we say if del cross f equals 0, we say f is irrotational. We can think of the curl as being related to the tendency of the field to cause a rotation. So if you're thinking of a velocity field in a liquid, the curl tells you that the tendency of the liquid to rotate. But we'll go into more detail at the end of the chapter. All right. So let's look at an example. So if we wanted to find the curl of f of x, y, z, x squared z I hat minus 2x z j hat plus y z k hat. That's a pretty complicated vector field. Not complicated in terms of how we write it, but I think it would be hard to visualize. Y z k hat. So the curl del cross f is going to be this vector. Take the partial with respect to x, partial with respect to y, partial with respect to z of x squared z minus 2xz and yz. And we're going to just perform this operation. So we get I hat, and then we take the determinant of the matrix we get when we cross this row and this column off. So we take the partial with respect to y of yz, so we get z. And then we take the partial with respect to z of minus 2xz, and we subtract, so that's minus 2x. Minus j hat, remember that minus sign. Now we're going to cross out this column and this row. So we take the partial with respect to x of yz, 0, minus the partial with respect to z of x squared z, x squared, plus k hat, times, we'll cross out this row and this column, partial with respect to x of minus 2xz, minus 2z, minus, and then we get the partial with respect to y of x squared z, 0. So we get that the curl is 2x plus z I hat plus x squared j hat minus 2z k hat. That would represent the curl of that vector field. And this vector tells us something about the tendency of that field to cause a rotation. It depends. And what we're going to end up doing is integrating the curl of the normal component of the curl over a surface.
Oh, good.
What is that? Go back.
I don't know.
So all of these things that we're talking about, the gradient, partial derivatives, multiple integration, they all, normal vectors, they all get mixed together into a single problem. All right, the test for conservative vector fields in space. Well, based on what we've talked about, you might guess what it is. If we say f of x, y, z equals m I hat plus n j hat plus p k hat. This is conservative if and only if, and just a reminder, if and only if means my statement works both ways. It's conservative if this is true, and if this thing is true, then it's conservative. If and only if del cross f equals 0. And this is equivalent to, this means the partial of p with respect to y equals the partial of n with respect to z. The partial of p with respect to x equals the partial of m with respect to z. And the partial of n with respect to x is equal to partial of m with respect to y. And these all have to be true because of the equivalence of mixed partials.
So hang on, didn't you just say the del cross f equals 0 is irrotational?
Yes.
Is that
An irrotational field is conservative.
also conservative?
Yes.
And if it's conservative, it's also irrotational?
Yes.
Okay. Oh, that's cool. So those two terms are interchangeable?
Yes. Irrotational and conservative. And the curl is 0. All three things mean the same thing. All right, so for this next problem, I want to set it up. I want to talk about the problem-solving procedure, but we're not going to go through the process. So our test for conservative vector fields in space is the curl equal to 0 vector? Equivalence.
Oh, there's two blue ones. Sorry.
All right, so if you have a problem, if f is conservative, not if, is f conservative? If so, find a potential function.
Can you like just scroll back to the last page and so I can see the last line? Okay, thanks.
All right, so I'm going to say that our function, our vector field, is y squared z cubed I hat plus 2x y z cubed j hat plus 3x y squared z squared k hat. So I just want to talk about how we would go about solving this problem. I don't want to go through all the process. So how do we try if this is conservative? So for part one, we see is del cross f equal to 0, the 0 vector. So we find the curl. I'm going to tell you in this case, it is. It takes a little calculation. So what do we do then to find the potential function? Integrate the components. So if I called this first component m, second component p, n, third component p, we would do the integral of m with respect to x, the integral of n with respect to y, and the integral of p with respect to z to find our potential function. And this turns out nice, and all we have to, we just get one term when we integrate this with respect to x, y, and z. And if you look, it's pretty easy to see what the potential function is going to be. What does it come out to be? X, y squared, z cubed, plus a scalar constant.
Yeah, go back.
I did C just to make us happy.
Yay.
Okay, but like, is that the same C as the K before?
Yes.
Yeah.
Just
It's just a scalar constant. Just your plus C.
it's not, so, hang on, where did the C with the vector go? That was, we had that for a while, does that have to come back to?
No. Because that had to do with integrating a vector valued function.
That was,
So here we're integrating the components of the function. Right. All right, there's one more operation that we need to talk about today. So we know about the curl. We also need to know about the divergence.
oh, good.
More.
How long is this?
Not too long.
Can I go back to
If we have a vector field in the plane, the divergence of f, written, we say div f for divergence equals del dot f. And that's going to be the partial of m with respect to x plus the partial of n with respect to y. This is the dot product. And the divergence,
Would this other have a z component too?
yeah, so we're going to write that next. So we have m I hat plus n j hat plus p k hat. What looks too much like 0? Oh yeah, O ends up looking. Divergence of f is del dot f, and that's just going to be the partial of m with respect to x plus the partial of n with respect to y plus the partial of p with respect to z. And the divergence is a scalar. So this is similar to finding the gradient. Well, we find the gradient of a scalar field. We find the divergence of a vector field.
Can you say that again?
So for the gradient, our del operator operates on a scalar. For the divergence, our del operator is dotted with a vector. So that's the difference. It operates on a vector this way. So the divergence is a scalar, and the divergence of the curl is always equal to 0. So we're saying del dot del cross f is 0.
Not a 0.
It's a scalar. So the divergence of the curl is 0. The divergence tells us the tendency of a vector field to flow outward. To diverge. Yeah. But we'll make that more technical at the very end of the chapter.
To go away.
All right, I just want to look at one example of calculating the divergence. No, that's not the one I want.
Can we check for conservative fields? Divergence?
No. The divergence is definitely easier to calculate than the curl. All right, we want to find the divergence. Find the divergence of f. Well, the divergence of f, div f, is del dot f. So we take the partial of the x component with respect to x, 2x, partial of the y component with respect to y, 2xz. Oh, we did remember how to take partial derivatives. Plus the partial of the y component with respect to y, 0, plus the partial of the z component with respect to z, y. So the divergence is 2xz plus y.
What does that mean?
It has something to do with the tendency of that field to flow outward.
Okay.
We have to wait to give a more technical interpretation to the divergence and curl until the very end of the chapter, because we need a lot more tools.
Isn't it kind of like how in Calc 1 we have the curvature thing, the second derivative test, and all we were looking for was whether it was positive or negative,
Right.
or was actually consistent with it and actually being associated with the value.
Right.
So it's just kind of that. It's like, here, this exists.
So can you have like values in a problem that you would plug into your final answer to see how far it would go out?
Yeah.
What would it say if the divergence would be 0?
Then the field doesn't tend to flow outward from a surface.
So that means
No, then the divergence would be negative. If it flows inwards, it would be negative.
it just doesn't do anything.
So what would that look like?
Wouldn't it
Well, if it were circulating, the divergence of the curl, right? So it's not flowing outward. So like in your sink, when the water goes around the drain, that doesn't have very much divergence. Yeah? Divergence is related to flux. We will use divergence to talk about flux. Yes, that's a good observation.
This hyperbolic trig gonna be on the front. Are we gonna have like we have to find like del f with a hyperbolic trig function? I'm gonna try. I'm going to try.
The derivatives are easy.
Keep writing them, I'm just not going to do them all.